Dear students, in this section we are going to discuss different cases of an ideal gas when it's confined in any closed container. Here we are going to learn the application of the first law of thermodynamics, application of the ideal gas equation along with adiabatic equation. And this we are going to learn through some selected illustrations. So let us move to illustration number 1. In first illustration, we are given two containers, and these two containers contain two samples of an ideal gas initially at same temperature and pressure, and they are compressed from volume capital V to V by 2, half the volume. You can observe here this container number 1, this is the diathermic container and this is the adiabatic container. In diathermic container, walls are made of conducting material, and in adiabatic container, walls of the container made of some insulating material, and this piston is also made of the insulating material. In diathermic container, there is interaction of the heat from surrounding to sample of the gas, that is inside the container, right? That means the temperature outside and inside always remain same in this case because the process is done slowly. In adiabatic container, there is no interaction of the heat from outside to inside. That is, there is no outflow or inflow of the heat from system to surrounding or surrounding to system. In the first case, the process is isothermal, and second case, the process is adiabatic. And we need to find or we need to investigate in which sample is the pressure greater. Okay. So let us move to analysis part. These are the two containers, and here V initial equal to V. Let us assume the initial volume in the both cases V, and final volume is half the initial volume, that is V by 2. That means the ratio of the initial volume to the final volume can be written as V initial to V final equal to 2. Okay. In isothermal case, we can apply P1 V1 equal to P2 V2, or P initial V initial equal to P final V final, right? And here we can write P final equal to P initial V initial divided by V final, right? After substituting the value, we can write the final pressure in this case is equal to twice the initial pressure. Now for the adiabatic container, we need to apply adiabatic equation. We are given the relationship of the volume, this is the initial to the final volume, and we need to make the relationship of the pressure. That means in case of the adiabatic process, we need to apply P initial V initial to the power gamma equal to P final V final to the power gamma. That means from this relation we can write P final equal to P initial multiplication V initial to divided by V final to the power gamma, right? And we know this gamma is always greater than 1 in case of the adiabatic process. That means this ratio, we know this is equal to 2, right? That means 2 to the power gamma is greater than 2. This is 2 to the power 1 and this is 2 to the power gamma. That means pressure in case of the adiabatic container will be greater than the diathermic container. That means the pressure in the adiabatic pressure is greater, right? This is the pressure in adiabatic container will be greater. Okay. Now let us move to next illustration. In this illustration, two vessels A and B of equal volume V naught are connected by a narrow tube which can be closed by a valve. This is a narrow tube and this is a valve. The vessels are fitted by pistons. These are the pistons, and which can be moved. Pistons can be moved to change the volume of the vessels. That means we can change the volume of the both vessels by these pistons. Initially, valve is open. Initially, this valve is open. That means both vessels A and B are interconnected, and it is given the gas in the container have the adiabatic constant that is equal to Cp by Cv equal to gamma. and it is also given atmospheric pressure. Gas is at the atmospheric pressure P0 and atmospheric temperature T0, and initially valve is open. Okay. Now it is given the walls of the vessel A are diathermic. Valve of this vessel is diathermic. That means these walls are made of the conducting material, and that of B are adiabatic. This is adiabatic container. Valve is now closed. Now this valve is closed after opening for the sufficient long time. Valve is closed and piston is slowly pulled out to increase the volume of the vessel double the original volume. Now this valve is closed and the volume of this vessel and volume of this vessel is increased to 2V0 and 2V0. In the first part of the question, we need to find the temperature and pressure of the two vessels, and in the second part of the question, it is given the valve is now open. That means this valve is again open for the sufficient long time, so that the gas acquired the common temperature and common pressure. Find the new value of the temperature and pressure in this case also. Okay. Analyze the first case. First case is what? Initially valve is open, then we close the valve and increase the volume. So let us move to analysis part of the first part. This is the diagram when valve is closed. Okay. When valve is closed, the initial pressure is P0. Initial pressure here is also P0. Initial volume is V0. Initial volume here is also V0. Initial temperature is T0 and initial temperature is T0. Okay. This is the situation just after closing the valve. Now what happens? Now the piston move to increase the volume. That means volume of this container A, which is diathermic, is increased twice the initial volume, and volume of this adiabatic. Now this container is adiabatic because valve is closed. Now this container is separated from this and also from the surrounding. So let us first analyze the first diathermic container, right? In diathermic container, what will happen? The temperature of this gas, that is T0 initially, will be same as the surrounding. That means temperature of this container is not going to change. That means we can apply the equation P1 V1 equal to P2 V2, right? And here initial P1 equal to P0, V1 equal to V0, and valve pressure we need to calculate. Say this is P2 and this is twice V0. Now we got the final pressure in this situation, that is P0 divided by 2. Okay. And we know this is diathermic container. That means temperature of the gas inside the container will be same as the surrounding. That means final temperature of this container will be equal to T0. Now consider this adiabatic container. Initial state of this adiabatic container is temperature T0, volume V0. Final state, volume 2V0, temperature we need to calculate. We have adiabatic relation in term of the temperature and volume, that is T V to the power gamma minus 1 equal to constant. That means now we can apply the adiabatic equation like this, that is T1 V1 to the power gamma minus 1 equal to T2 V to the power gamma minus 1, right? Now initial state T0, initial state of the volume V0, this we need to calculate. This is 2V0. So let us substitute the value. Now we got the value of T2, T2 equal to T0 multiplication 2 to the power gamma minus 1, right? Now we need to find the pressure. Again we can use the adiabatic equation. Adiabatic equation in terms of the volume and pressure is PV to the power gamma equal to constant, and here we can write P0 V1 to the power gamma equal to P2 multiplication V to the power gamma, right? And this we can substitute. This is V0 and this is 2V0. So we got the value of P2. P2 is equal to P naught divided by 2 to the power gamma. This is the final pressure. Now let us move to next part of the question. In next part of the question, it is given the valve is now open for sufficient time so that the gas acquired the common temperature and pressure. Find the new value of the temperature and pressure. And we know when we open the valve, right? Suppose this is the initial situation before opening the valve. This container was separated from this container. Now if we open the valve, this container will be in contact with this container. Now this container is no more adiabatic because this is connected with this diathermic container, and diathermic container can exchange heat from the surrounding, right? And because this is diathermic, that means the temperature of the gas in the container will be the same as the surrounding. That means the final temperature of this container should be equal to T naught, which will be the same as the temperature of the surrounding. And because this container is connected by this tube, that means final temperature of this should also be T naught. That means final temperature will remain T naught throughout, we can say, right? And also both are interconnected. That means the final pressure of both gas in the both container or both vessel will be same. Let us assume this value as P. That means P1 equal to P2 equal to P. And both are interconnected. We can say total volume will be equal to 2V naught plus 2V naught equal to 4V naught. And as we discussed, temperature of the both container will be equal to temperature of the surrounding, that is equal to T naught. Okay. Here we can say the number of the moles at initial state and final state will be same. And initial number of the mole before closing the valve, we know this is P naught multiplication V and V 2V naught divided by RT naught. So initial number of the moles, or we can say number of the moles at initial state equal to P naught 2V naught divided by RT naught. Okay, now we open this. That means initial pressure is P. Initial volume is 4V naught. Final volume is 4V naught. And final temperature T naught. Now we can apply the ideal gas equation PV equal to nRT. So here we can write P multiplied by 4V naught equal to nRT naught. Right? From this equation we can find the value of P, because we know the value, right? We know the value of N, that is P naught 2V naught divided by RT naught. So we got the value of P equal to P naught divided by 2. That is final pressure is same as the half the initial pressure. Okay.